This is fourth module of chapter 7. In the previous module, we discussed Euclidean domains and principal ideal domains. In this module, we will characterize unique factorization domains, which are the integral domains in which every non-zero non-unit element can be expressed as a product of irreducible elements uniquely in some well defined sense. Also, we will show that in a unique factorization domain, an element is prime if and only if irreducible. And finally, we will characterize the special features of the polynomial rings over a unique factorization domain. First, let me define factorization domain. An integral domain D is said to be a factorization domain if every non-zero non-unit element A of D can be expressed as a product P1, P2, Pn, where these Pi are irreducible elements in D. And a unique factorization domain is a factorization domain where such factorizations are unique up to associates and order of the irreducible factors. That is, if P1, P2 up to Pm is equal to Q1, Q2 up to Qn are two irreducible factorizations of a same element A, then we must have M is equal to N and there is a permutation sigma such that each Pi is an associate of Q sigma I. It is easy to observe that the ring of all integers Z is a unique factorization domain. In this chapter also we will prove that every principal ideal domain is a unique factorization domain, and in the final step of this module I will give an example of a unique factorization domain which is not a principal ideal domain. First, let me prove that in a unique factorization domain every irreducible element is prime. Since we already have in an integral domain every prime element is irreducible, it follows that in a unique factorization domain an element is irreducible if and only if it is prime. So, to prove that every irreducible element is prime, let us consider an irreducible element P from D. To prove that P is prime, suppose that P divides AB. We are to show that either P divides A or P divides B. Since P divides AB, we have some C in D such that AB equal to PC. If A is equal to 0, then P divides A, and if A is a unit, then B equal to P A inverse C shows that P divides B. Similarly for B. Thus, we can assume that both A and B are non-zero and non-unit. Then AB equal to PC implies that C is not equal to 0 because we have assumed that neither A nor B is a 0 and it is an integral domain. Also we show that C is not a unit, otherwise PC is irreducible, that is A into B is an irreducible element, which implies that either A or B is a unit, but we have assumed that neither A nor B is a unit. So, it follows that C is not a unit. Thus, we have A, B and C are neither 0 nor units, and since it is unique factorization domain, so all these three elements A, B, C have 3 unique irreducible factorizations. Assume that they are A1, A2 up to AR, for B it is B1, B2 up to BS, and for C it is C1, C2 up to CT. Then AB equal to PC implies that A1, A2 up to AR into B1, B2 up to BS is equal to P into C1, C2 up to CT. Since D is an unique factorization domain and here the elements in these products in both sides are irreducible elements, so P must be associate of one of the irreducible elements A1, A2, AR, B1, B2, BS. If P is an associate of some AI, say AI equal to PU, where U is a unit, then A becomes equal to PU A1, A2 up to AI minus 1 into AI plus 1 up to AR, which shows that P divides A. Similarly, if P is an associate of some Bj, it follows that P divides B. Thus, P becomes a prime element. Now, we show that GCD exists in UFD. Let A and B be two non-zero elements in a unique factorization domain D. Then we show that GCD AB exists in D. The technique in the proof we will use here essentially same as the technique in the ring of integers. That is the technique we use to find GCD of two positive integers. Recall that if we are to find GCD of two integers, then first of all we express the integers as a product of prime integers, and then according to the power of the prime factors we get the GCD. Suppose A is P1 to the power L1, P2 to the power L2 up to PR to the power LR. This is the irreducible factorization of A, and assume that the irreducible factorization of B is P1 to the power M1, P2 to the power M2 up to PR to the power MR. Note that it may be that there are some irreducible factors of A which may not be factors of B. In this case, we consider the power of these irreducible factors as 0. That is, what I want to say is that sum of L1, L2 up to LR, M1, M2 up to MR may be 0, and we assume that P to the power 0 to be the unity of D. So, if we take Ni to be the smallest among Li and Mi, it is easy to prove that the element D, which is the product of P1 to the power N1, P2 to the power N2 up to PR to the power Nr, will be the GCD of AB. The most interesting fact is that though GCD of two elements exists in a unique factorization domain, but the Bezout's identity does not hold here, which I will show by giving an example in the end of at the end of this module. Recall that every Euclidean domain is a principal ideal domain. Now, I search for the interrelation between principal ideal domains and unique factorization domains. We will show that every principal ideal domain is a unique factorization domain. We proved that every Euclidean domain is a principal ideal domain with the help of division algorithm. Here I prove this using every irreducible element is prime. First we prove some lemmas. Our first lemma states that every ascending chain of ideals in a principal ideal domain is finite, that is of finite length. Let D be a principal ideal domain. Since D is a PID, so every ideal of D is generated by some single element. So, we can consider an ascending chain of ideals in D as the ideal generated by A1 is contained in the ideal generated by A2 and so on. Now, the union of all these ideals is an ideal. In general, the union of ideals may not be an ideal, but since here the ideals we are considering forms a chain, so their union must be an ideal of D, and since D is a principal ideal domain, so the ideal I is also generated by some element A. Here our main strength is that since I is the union of all these ideals, that is ideals generated by AI, so A must be in some ideal in this chain. Assume that A is in the ideal generated by AK. Then we have the ideal generated by A is a subset of the ideal generated by AJ for all j greater than equal to k. Also, the ideal generated by A being the union of all ideals of the form ideal generated by AJ, we have ideal generated by AJ is a subset of ideal generated by A. Thus, we have the ideal generated by A is equal to the ideal generated by AJ for all j greater than equal to k. Thus, the sequence of ideal we consider is finite. Now, we prove that a factorization domain is a unique factorization domain if and only if every irreducible element is prime. We already have in a unique factorization domain every irreducible element is prime. It remains to prove that if in a factorization domain every irreducible element is prime, then it becomes a unique factorization domain. So, consider a factorization domain D in which every irreducible element is a prime element. Since D is a factorization domain, every non-zero non-unit element of D has an irreducible factorization. It remains only to show that this factorization is unique up to associates and order of the factors, and we will prove this by induction on the number n of irreducible factors in irreducible factorizations of an element. If n equal to 1, then the result follows from the definition of irreducible elements. And let us make our induction hypothesis that the result is true for all n less than s. Suppose A belongs to D is such that A is equal to P1, P2 up to Ps, which is equal to Q1, Q2 up to Qt. That is, the element A has two irreducible factorizations, one of which contains s factors. Now, it is given that every irreducible element in D is prime. So, since Ps is irreducible, it is prime, and Ps divides Q1, Q2 up to Qt, and since Ps is prime, this implies that Ps divides some Qi, which we may assume to be Q2 upon rearrangement. Since both Ps and Qt are irreducible elements in D, this implies that Qt is an associate of Ps, that is Qt will be equal to Ps into some unit u. Then we can cancel Ps from both sides and get P1, P2 up to Ps minus 1 is equal to Q1, Q2 up to Qt minus 1 into u. Since Qt minus 1 is an irreducible element and u is unit, we have that q t minus 1 into u is an irreducible element. So, the both sides are irreducible factorizations of some element. So, by induction hypothesis it follows that s minus 1 is equal to t minus 1 and each pi is associate of some qj, and thus the result follows. Now, we have the main theorem that every PID is a UFD. In a PID, we have proved that every irreducible element is prime, and just now we have proved that a factorization domain becomes a unique factorization domain if every irreducible element is prime. So, it is sufficient to show that every principal ideal domain is a factorization domain. Let D be a principal ideal domain and A belongs to D be a non-zero non-unit element of D. We have to show that A can be expressed as a product of irreducible elements. If possible, on the contrary, assume that A is not a product of irreducible elements. Then we have two elements A1 and A1 dashed in D, neither of which is a unit such that A equal to A1 and A1 dashed. If both A1 and A1 dashed have irreducible factorizations, then we would have some irreducible factorization of A. So, either A1 or A1 dashed does not have any irreducible factorization. We assume that A1 is not a product of irreducible element. Since A1 dashed is not a unit, we have the ideal generated by A is a proper subset of ideal generated by A1. Since A1 is not a product of irreducibles, similarly we get some A2 in D such that ideal generated by A1 is a proper subset of ideal generated by A2 and A2 is not a product of irreducibles. We continue and get a strictly ascending infinite chain of ideals in this way. This contradicts that D is a principal ideal domain, because in a principal ideal domain every ascending chain of ideals is finite. Thus, our assumption that A cannot be expressed as a product of irreducibles is wrong, and it follows that A has an irreducible factorization. Now, we consider polynomials over a unique factorization domain. Recall that Z is a PID, but the polynomial ring Zx is not a PID. Here we show that if D is a unique factorization domain, then the polynomial ring Dx is also a unique factorization domain, and hence it follows that the polynomial ring Zx is a UFD. Thus, Zx will be an example of a unique factorization domain which is not a principal ideal domain. First, we define content of a non-zero polynomial. Let D be a unique factorization domain and Fx be a non-zero polynomial on D. Then GCD of A0, A1 up to An is called content of Fx, which we denote by Cf. Note that since Fx is a non-zero polynomial, some Ai are non-zero, and in a unique factorization domain GCD of non-zero elements exists. So, always content Cf of a non-zero polynomial f(x) exists in D. But since GCD is not unique in a unique factorization domain, content of a polynomial is also not unique, and we know that relation between two GCD is that they are associates. So, we have contents of a polynomial are associates to each other. Now, we define primitive polynomials. If D is a unique factorization domain, then a non-zero polynomial f(x) is called primitive if its content is a unit. Now, we show that every non-zero polynomial over D can be expressed as, say, f(x) is a non-zero polynomial, then it can be expressed as f(x) equal to content of f into some primitive polynomial f(1)x. Consider f(x) as a0 x to the power n plus a1 x to the power n minus 1 up to a n in dx, and which is non-zero. Then some ai are non-zero, and so GCD of a0, a1, an exists in D. If D is a GCD of a0, a1 up to an, and ai is equal to D into some ai dashed for all I, then we have GCD of a0 dashed, a1 dashed up to an dashed is equal to 1. Thus, f(1)x is equal to a0 dashed x to the power n plus a1 dashed x to the power n minus 1 up to an dashed is primitive. So, f(x) becomes content of f into f(1)x. It can be proved that product of two primitive polynomials is primitive. Details of the proof is given in the e-content. Also, we have if f(x) belongs to Rx is a non-constant primitive polynomial, then irreducibility of f(x) over R implies irreducibility of f over Qr, where Qr is the quotient field of R. With the help of these two results, we can prove that if R is a unique factorization domain, then the polynomial ring Rx is also a unique factorization domain. Thus, since Z is a unique factorization domain, we have the polynomial ring Zx is a unique factorization domain. Using the UFD Zx, I will conclude this module by showing that Bezout's identity does not hold in a UFD in general. Consider two polynomials x plus 2 and x plus 4 from Zx. Then it is easy to observe that their GCD is 1. I show that 1 cannot be expressed as x plus 2 into f(x) plus x plus 4 into Gx. If possible, suppose there are two polynomials f(x) and Gx in Zx such that one is equal to x plus 2 into f(x) plus x plus 4 into Gx. Comparing the constant terms, we get 1 is equal to 2 into a0 plus 4 into b0 for some a0 and b0 in Z, but which is not possible. Thus, in this module, we discussed unique factorization domains. In this domain, actually we considered the fundamental theorem of arithmetic, that is the property of the integers that every integer greater than 1 can be expressed as a product of prime integers. Recall that The unique factorization domains are the integral domains in which every non-zero non-unit element can be expressed as a product of irreducible elements uniquely up to associates and order of the factors. We have shown that every principal ideal domain and hence every Euclidean domain is a unique factorization domain, and also show that the polynomial ring ZX is a unique factorization domain, but not a principal ideal domain. So, there are examples of unique factorization domains which are not principal ideal domains. But I think the most important fact to remind is that though GCD of two non-zero elements exists in a UFD, but Bezout's identity does not hold here.